So good morning to all. Myself M. Soundararajan, Assistant Professor from Department of Agricultural Engineering at Sri Shanma College of Engineering and Technology. So today class is about soil water. So in this lecture we're going to see the classification of soil water and then different movement of soil water occurring in the soil flow profile. So these are about our today class. We can to move next slide. Yes, I given here the definition for soil water. So soil water is the water held in the pore spaces between the soil particles and around them. So the water present around the soil particles or present the water between the soil particles. Okay, so that's called the soil water. So this makes a thin film on the particle surfaces. Okay, so if the soil particles is like imagine that if this is the soil particle, the water is presented between the soil particles. Okay, the water present in between the soil particles. Like the line defines the denotes that the soil water. So this is the soil particle. This soil particle two. This soil particle three. So one, two, three. So in between the soil water is presented. Then or around the surface of the soil particles also water is presented. So this water is called soil water. So it acts as a medium for nutrient dissolution and then root uptake purpose and most biological activity in the soil. So these actions are done by soil water. Okay, so here in this picture you can see that how soil water systems in the cyclic process. So first the precipitation occurs, the water comes from above, then it reaches the ground surface. Some water penetrate to the ground and some water available at the upper portion of the earth. So that is called the soil water, that is colored in dark blue color. For your understanding, this is the soil water that is available upper the earth crust for the plant growth. So that is the soil water. Okay, so here the different terms you can see, that evapotranspiration, surface runoff, and stream flow of the water. So the water in different forms is uh, given in this pictures, that is named in this named in different names. Okay, we can move to next slide. I hope that you understood what is the soil water. So next one is the classification of soil water. So based on the physical and biological uh, view, we classify the soils into different types. That are the in physical types. We going to see that what is the gravitational water. So gravitational water is nothing but the water is flow in the soil profile through by the gravitational force. Okay, the first gravitational water occupies large pores that are non-capillary pores immediately after heavy rain or irrigation and saturates the soil. So the gravitational water occupies the macro force. Occupies yes, macro force or large pores immediately after heavy rain or irrigation and saturates the soil. And this gravitational water held at very low tension, that is at the pressure in the pressure range of potential higher than about 0.012 to 0.03 megapascal. So is that better than field capacity, so it drains the downward under the gravity if there is drainage. So the gravitational water remains in the profile only for short time, generally not available to plants because it moves too quickly past the root zone and also creates anaerobic condition if it stays in the soil. The next type is the capillary water. So capillary water is nothing but it is the it this capillary water occupies in the micropores. Okay, so it's not like gravitational water. So capillary waters are seen in the micropores. So and it forms continuous films around soil particles after gravitational water has drained. Okay, so capillary water held by capillary and surface forces at intermediate tension, that roughly between field capacity and permanent melting point, about 0.03 to 1.5 megapascal. Uh, then the capillary water in mobile in liquid form and is in the main fraction available for plant uptake. So roots absorb these water from the films and small pores. So capillary waters the are available for plant usage. The next one is the hygroscopic water. Okay, I marked that hygroscopic water. So hygroscopic water is a very thin water film. Okay, tightly absorbed onto particle and collide surfaces. So even when soil appears air dry, so the hydroscopic water held at very high tension, often less than 3 megapascal down to about 100, minus 3 megapascal down to about minus 100 Pascal or more, so the roots cannot remove it. So not these hygroscopic water not available to plants and behaves more like water bound in the solid than free liquid water. So because of the pressure range like 3 megapascal and 200 megapascal that are very strong to enough uh, that are enough to bind the soil water to the with the particles. Okay, so these hygroscopic waters are not available to plants and behaves more like water bound in the solid than free liquid water. The next one is the chemically combined water. So the chemically combined water means the water that is part of mineral structures or hydrated oxides, so released only on heating to high temperature. So this chemically combined water for completeness not considered soil moisture and is unavailable to plants. So apart from these four type, there is one another type is majorly taken by the scientists, that is the film water, that is not classified in this slide. So except these four, the type of physical classified water, there is another one type is the film water, that is majorly taken by the different uh, peoples or scientists. That film water uh, as the is the thin layer between capillary and hygroscopic water. So the part of this film is available and not part becomes unavailable as tension increase. So part of this film water is available to plant growth and part of the some part of the film water is not available to the plant growth. Okay. Then biology. Next one is the biological classification. In the biological classification, there are three types. First one is the available water. So based on the availability of the water to the plant, we classified uh, these types. So biological classification mainly based on plant availability, the water availability to the plants. So from a plant point of view, soil water is often grouped as available water, unavailable water, and excess water. These three types. So first one is the available water. Mainly capillary water held between field capacity and permanent wilting point, which roots can absorb. So the water that is hold between the field capacity, I shortly given as the FC, field capacity and permanent wilting point. PWP, permanent wilting point. So in this pressure range, the water is available to the plant growth. That's why it is called available water. The next one is the unavailable water. So the unavailable water means the hygroscopic water, chemically combined water, and the fraction of water below the permanent wilting point, which plants cannot extract. So below the permanent wilting point, okay, below the permanent wilting point, the plant cannot absorb the water. So the example for unavailable water is the hygroscopic water and chemically combined waters are some example for the unavailable water. Then the third type is the excess water. The excess water is that gravitational water. So gravitational water is the example for excess water. So gravitational water in large pores that drains quickly and can cause the poor aeration if it persists. Okay. The next one is the we can move to next slide. So in this slide, I compared the three physical classified waters that are gravitational water, capillary water, and hygroscopic water. These three types are compared in order to different aspects that are pore size occupied and retention force and typical potential range of water available those water available to the plants and residence times in the profile and aeration effects. So these are with view of these aspect, these three types of physical classified waters are compared in this slide. Uh, we can see one by one. The first is the gravitational water is present in the large pore size. In the large pores, these gravitational waters is available. These large pores are called as the non-capillary pores. Then capillary waters is present in the microphores. Okay, so these microphores are called, called as the capillary pores because the water present in the capillary pores is called capillary water. Then hygroscopic waters are present in the surface of the soil particles or in the colloidal forms. Okay, so this is the first aspect or character parameter, that is a pore size. So based on the water present in the different sized pores, this water is named in different names. Okay. Then next aspect is the retention of the force, retention force that that act on these three waters. Okay. The first one is the retention force that is very weak in gravitational force to hold that gravitational water because gravity is dominated in gravitational water. That's why that gravitational water is quickly drains downward to the water table. Okay. Then next one is the capillary water. Here the capillary forces plus with the help of surface forces makes the capillary water to hold within the soil profile to make available for the plant growth. Then hygroscopic water is the strong absorption forces make the makes the soil uh, particles and water to be combined. Okay, this strong absorption force makes that water to absorbed in the surface, absorbed within the soil surfaces. Then type is the type potential range. The above the field capacity and almost near to the 0 megapascal are the pressure range to the gravitational water. That means act on the range act on gravitational water. That means that there is no pressure. Okay, that's why the 0 megapascal act force force act on the gravitational water. That's why this gravitational water is uh, drains or flow freely in the soil profile without any disturbance of a pressure range. Then next one is that capillary water. The capillary water, the range potential range between 0.032 minus 0.032 minus 1.5 megapascal. That's why this water is can be hold in the soil part in the soil profile soil or in soil that available to the plant growth. Then next one is the my hygroscopic water. The potential range for hygroscopic water is the less than minus 1 megapascal. That is very low or very low. So that's why this hygroscopic water is not available for the plant growth. And next is the availability to the plants. Generally, these gravitational force are not available to the plants because it is not stay on the upper portion of the soil. It flows up downwards. That's why it goes far away from the plant roots. So it is not available to the plants. Then next one is that capillary water. So capillary waters are mainly available to the mainly available sources to the plant growth. So these water is the main source of the plant growth that available for root absorption for the growth. And hygroscopics as well as gravitational water, it also not available for the plant growth. Then residence time, that is the time retention time or residential time in the soil profile is the very short period only. The gravitational water available in the soil profile because of it drains quickly. Then capillary water is the moderately available in the soil profile that governs the plant growth period. Then hygroscopic waters are present to the long period of on the surface of the soil particle because it persists as hair dry moisture. Then the next aspect is that aeration effect. The gravitational water can cause the anaerobic conditions because there is no water present because the waters are flowly downwards, making the upper portions are void uh, with hair. Okay, so it makes the void full of air. Then capillary water is the usually optimum aeration at the field capacity. Then hygroscopic waters not affect on aeration because it not participate in the um, or not participate or not present in the void spaces. So it don't affect that aeration, the airflow of the soil. We can move to next slide. So next one is the soil moisture constant. That is the based on the pressure ranges that's our uh, potential ranges. The soil constants are derived by the research. So the first one is the field capacity. The water content remaining 1 to 3 days after heavy rain or irrigation when gravitational water is drained and downward flow becomes slow. So that is the after the gravitational water is drained and downward flow becomes slow. The water available for to the 1 to 3 days in this potential range, that is the field capacity. See, it represents upper limit of the water that soil can hold again hold the water against the gravity. It's the very important. So in field condition water is hold against the gravity, so the water can flow downwards. So it's a practical upper limit for plant available water. Then the next one is the permanent wilting point, the PWP, the water current at which plants remain wilted and do not recover even if placed in the saturated atmosphere. So this corresponds to soil water potential about minus 1.5 megapascal. This is very important. Below this, roots cannot extract the water. So up to the PWP potential range, the roots can absorb the water. Then below the permanent wilting point, roots cannot extract the water from the soil. So the next one is the available water capacity, that is abbreviated like AWC. So defined as AWC is gained by subtraction subtracting a PWP value from the field capacity, then the water stored between the FC and PWP is described as available water capacity. So this range determines how much water given soil can supply to the crops between the irrigation or rains. So here the pictorial representation I given for your understanding. So in the saturation, pores are full of water, gravitational water is lost. Okay, so the pores filled with water. You can see the pore means the space between the two soil particles. So the it's a soil particle one, it's a soil particle two that are in brown color. So these are brown colored uh, brown cloud or soil particles. The space between each soil particles are called the pore spaces. So that is filled with water. That's why the water filled in the space is given in the blue color for your understandings. So these are the downward droplet movement denotes that the gravitational water flow downwards. Okay. Then in this picture you can see the field capacity, the water available to the plant growth. So water not drain downwards as like in the saturated condition. So the water is held between the soil particle. So that's why this water is available to the plant growth. Then the next is the condition between the field capacity and wilting point. This also is like the small amount of water and air presented in the pore spaces. So combination with air and water. So the little amount of water present for the plant growth when compared with the field capacity. The next one is the wilting point. The water is only seen on the surfaces of the soil particle. You can see that the blue color uh, line is on surrounded on the soil particles. For your understanding, that's blue color is the soil water. So the water is presented on the surfaces of the soil particles in the wilting point condition. That means no more water is available to the plant. So here the charts given to the for your easy understanding. So at 0 bars of pressure, the superflows of characteristics will be seen in this soil water, that is called saturated condition. Then in the zero at the 0.3 millimeter sorry 0.33 bars, um, that point is called field capacity. So then 15 bars is called wilting point. Then 31 bars is called hygroscopic waters. So above the hygroscopic water, there is no water present. That's why the soil is in the solid condition. Okay. Then between the superflow between the 0 to 0.33, the superflow is characteristics will be seen in the soil water. So the water flow freely from any direction in the any direction. So the in the between the field capacity and wilting point, the water is available at the soil that can be used by the plants. Or these are divided into two: the raw and sha. Raw means readily available water, then shaw means slowly available water. Then in between the wilting point hygroscopic point, the water will not available for the plant growth. Above the hygroscopic point, the water is not fully not available. That's why only soil particles can be seen that are in solid state. So there are different gravitation superflows condition. Gravitational water attains that capillary water are in the this range, like field capacity to hygroscopic water point. Then hygroscopic water is in between above the hygroscopic 31 bars. Okay, we can move to next slide. So in this slide we are seeing that movement of soil water. So soil water movement is described under the three types: the saturated and unsaturated and vapor flow. The first one, based on that, there are five types is given here: the infiltration, percolation, movement of the soil water, and saturation flow and unsaturated flow, and capillary rise. Capillary is the upward movement of the soil water in the soil. Then water vapor movement. So water vapor movement is the water, soil water in the form of vapor. That is the in the vapor form how soil is going. We will be seen in the water vapor movement. Okay. The first one is the infiltration percolation. Is the entry and downward movement of the soil. Okay. So first we have to see the infiltration. So infiltration is the entry of water from the surface into the soil pore spaces during the rainfall or irrigation. The infiltration rate depends on texture, structure, initial moisture, organic matter, and surface cover, and say slope, uncoarse structure, and well aggregated and covered soils have high infiltration. So the rate of infiltration will depend as I said, texture, structure, initial moisture, organic matter, surface cover, and slope of the soil. So coarse texture soil, well aggregated and covered soils have the high infiltration. The second one is the percolation. The percolation is the downward movement. Okay, the downward movement of water through the soil profile after it has infiltrated. Okay, so important for groundwater. The percolation is the important for the groundwater recharge, but can leach nutrients beyond the root zone when it excessive. Okay, the next one is the successive flow. The successive, you know that what is the infiltration and percolation. Now we're going to see the saturation flow. Saturation flow is that nothing but it occurs when all or almost all pores are filled with water. Okay, that is the saturated flow condition. So usually just after heavy rain or irrigation it occurs. So driving force is mainly gravity with some influences of pressure and potential gradients. So saturated flow rate is governed by the saturated hydraulic conductivity, which is higher in core structure soil with many large pores. The next one is the superflow unsaturated flow. So unsaturated flow means it occurs when pores contain both air and water. Is that under normal field condition between field capacity and permanent melting point. So movement is primarily due to the metric potential, that is the capillary suction gradients. Water moves from water zones to drier zones. I mean, water moves to from higher potential to lower potential places zones. So as soil dries, films thin, conductivity drops sharply, and the rate of unsaturated flow becomes very low. Okay. Then the next type is the capillary rise. Capillary is nothing but the upward movement of the water. Okay. The capillary rise is that in the presence of water table, capillary forces can lift water upward into the root zone. Okay. So height of rise in the greater in fine texture soil, but rate is slower in coarse soils. The rise is lower but faster. Okay, this upward flow can partially meet crop water demand in areas with shallow water table, reducing irrigation need, but also potentially bringing soils upward with that along with the water. The next one is the water vapor movement. So, water vapor. I'm going to mark that. Next one is the water vapor movement. The water vapor movement, when soil is very dry, liquid continuity breaks and the water moves mainly as vapor from moist to dry region and from cooler to warmer zones. So this process is generally slow but important in arid regions and near to the soil surface under the strong evaporation. So these are the three different types of soil water movement. Okay, we can move to next slide. Okay, we came to end of this session. I hope that today concepts are understandable by all of you. I hope that you understood the concepts. So I will come with a new topic in next session. Thank you.